Welcome back, everyone. In this video, we're going to be departing from the derivative techniques, and we're going to start talking about what we can actually do with derivatives. And in this video, we're going to be talking about linear approximation, which is a technique of approximating a function using a straight line. And the reason you might want to do this is because linear functions are very easy to do computations with. And as the functions get more and more complicated, using an approximation will greatly reduce the computing time, whether you're computing things by hand or using a computer. And if I want to approximate a function at a point using a straight line, the best way to do that is by finding the tangent line at that point. And we've talked about finding tangent lines before, but we're going to be generalizing that process in this video. And as we know, the equation of a line in point slope form is y minus y1 is equal to m times x minus x1, where x1, y1 is 1 point on the line, and m is the slope of the line. And if I were to find the tangent line to a function at an arbitrary point, say when x is equal to a, I do know 1 point on that line, that being a, comma f of a. And I also know the slope of the tangent line because that's how we define the derivative. The derivative is the slope of the tangent line, and so the slope of this line would be f prime of a. And so I can go ahead and plug all those things in, and the equation of the tangent line at this point would be y minus f of a is equal to f prime of a times x minus a. And if I were to rearrange this and just solve for y, that would get me the equation here, and this would be the equation of the tangent line to the function f of x when x is equal to a. And once again, the idea here is that this tangent line will serve as a good approximation for the original function near the point that we found the tangent line at. So let's do an example. Let's say that we want to find the linearization of sine of x at x is equal to 0. And that word linearization is just the tangent line approximation to this function at the point x is equal to 0. And so this is the same tangent line from the previous slide. And we know that we want to find this when x is equal to 0. So let's go ahead and plug in 0, and now all we need to find are f of 0 and f prime of 0. And f of 0 is just taking 0 and plugging into the function, and that would be sine of 0, which is 0. And then the derivative of sine is cosine, and so f prime of 0 would be cosine of 0, and that would be 1. Now if I take those two values and plug them into the equation above where I should, it would get me that the linearization, the tangent line approximation of sine of x at x equal to 0 is y equals 0 plus 1 times x minus 0. And if I simplify that, it gets me the line y is equal to x. And so the real punchline here is that sine of x is approximately the function x near x is equal to 0. And while I'm a mathematician, I'm not a physicist or engineer, I have heard that in those fields, if we know that the value of x is close to 0, they will often replace sine of x with x because it's significantly easier to do computations with. Say, for example, I wanted to know what sine of 0.1 is. While using the tangent line approximation above, I could say that sine of 0.1 is approximately 0.1. And I can say this because 0.1 is pretty close to 0, and the above approximation is for any value close to 0. Now the actual value of sine of 0.1 is closer to 0.0998, but that means that our approximation is pretty darn good. 0.1 is very close to 0.0998, and it was significantly easier to compute. Now the further I get away from 0, the worse my approximation will be. Let's say, for example, we wanted to know sine of 1. Could we say that's approximately 1 using the above linearization? Well, the actual value of sine of 1 is about 0.8415. And the approximation of 1 is still close to that. This is still an approximation, but it is a significantly worse approximation than what we found for sine of 0.1. And just to demonstrate this point graphically, what you see here are the two functions sine of x and x, where sine of x is the function in red, and x is the straight line in blue. And we can see close to 0, these two functions are practically indistinguishable, which lines up with our idea that x is a good approximation for sine of x close to 0. But as I get further away, we can see that the approximation becomes worse and worse. Now, if you take the linearization of different types of functions, some of those linearizations will be better than others. And it will be better the closer the original function is to a straight line. Because what we're doing here is we're taking a curved function and we're using a straight line to approximate it. So if the function curves drastically at a point, the linearization will be worse than if it's closer to a straight line. And the way that we can measure curvature is with the second derivative, because that measures the concavity of a function at a particular point. Now, if the second derivative is close to 0, that means there's not a lot of curvature to it, and the linearization will be a better approximation than if the second derivative is far from 0. And going back to our example, with the function sine of x, the first derivative is cosine, and the second derivative is negative sine. And if I plug in 0 to that, that is negative sine of 0, and that's 0. And since that's not just close to 0, it is actually 0, this further reinforces how good of an approximation x is of the function sine of x near x equal to 0. And more often than not, the second derivative will not be 0, and we can use that information to determine whether our linearization will be an overestimate or an underestimate. If the second derivative is positive at a point, that means the function is concave up there. And if it's concave up, that means the linearization will be an underestimate of the function near that point. And looking at the graph above, the graph in red is the original function, and we can see it's very much concave up, and the linearization just can't capture that curvature, and so it's an underestimate of the function near that point. And for the same reasons, if the second derivative is negative, that means the function is concave down at that point, and the linearization will not be an underestimate, but an overestimate. And looking above, the function in red is a concave down function, and the linearization is very clearly an overestimate. And so if you were using the linearization in a real application, you would want to pick a point where the second derivative is close to 0.